Hello, welcome to the OMNeT++ routing project tutorial. In this video, I will analyze and demonstrate what mechanisms work on the routing protocol and how to use routing project to model various network topologies to perform static routing and analyze various traffic patterns using OMNeT++. Later, we will examine it by showing and analyzing one of the scenarios in routing project. After that, we will explain what we made to the routing protocol in various ways to enhance protocol performance and results. Afterwards, we will analyze results we obtained from changes we made in various ways. And also another detail to add about this presentation is traffic generators, routing logic, and query management are the main elements that we will analyze and show how they interact together in scenarios like store and forward, and cut through, etc. So these switching techniques. And so let's start our presentation by examining how Node.NET module works in our routing project. Why are we starting with Node.NET module? Because it has various relations to other modules. So let's start by giving basic definition. Node.NET module in OMNeT++ models all devices in network as compound modules called node, including hosts, switches, and routers. And so let's start by examining. It has parameters, int address and app type, string app type, and it has gates in out port. But most important things is submodules and connections we have. Submodules we have app, which inherits IApp, we will examine it later, and routing inherits routing, and query inherits L2 query with the size of port number. And start by app. It has parameters, address, which gets its parent address number. In the routing, we have gates in and out. We will see visualization later with the size of parent port. Why are we using that size of parent? Because it can be varying according to the scenario we have. And also query with the size of port. And let's start seeing design. As you can see, app connected to routing for local traffic with a both-way connection in and out, and routing connected with the L2 query for wiring inside the local node, which this is also two-way connection. Query, L2 query, in other words, query connects with the network ports, which is outside for transmitting traffic to the outside. Query should be linked to the other nodes ports. We will analyze it in connections. And as you can see, routing connections in and out. But important thing is here for loop with the size of port number -1, which we use size of ports because it can be varying according to scenarios. And in there, we make connections to the query to connect other nodes in network. As you can see, routing to query and query to other ports inside the network we have. So this is the Node.NET. So let's move to the IApp net file. In here, I want to start by giving basic definition and functionality of IApp. And it can be explained like modules that generate network traffic use IApp as common interface. As we use in here, it uses IApp as a common interface in the app. So, and it establishes the minimal structure that an application must have, the minimal structure defined in here, and guarantees that all apps can connect properly inside the network topology. This is the IApp.NET. So let's continue with the app module. So in app.cc module, I want to start with explaining fundamental purpose and functionality of app module is. Its purpose is basically creating network packets on a predetermined schedule. And I want to start by this part. It creates and assign its basic parameters. And then we have initialize and handle message functions. And I want to explain what these are doing. In the initialize function, after setting its parameters, it uses schedulate functions for initiate packet generation by scheduling self-message by using send AI time as a timeout value. And we have handle message. This is where all the things happen. We have two conditions, if condition and else condition. In the if condition, we have if message equal to generate packet. If message is generate packet, first we get a random destination from the destination address list and assign it. After that, we create unique name by using this block. Then we use packet creation in here and set all the necessary information to it. After that, we use scheduling self message by name generate packet, and we have else statement for handling incoming packets. For making it much more clear, I want to say that first if condition is for generating packet, as the name suggests. In other cases, it means we have incoming packet if in else statement. In this condition, we deal inside the else statement by emitting packet. For example, we checked and cast packet firstly for security, then we emit the signals we have, then delete the packet, incoming packet. Afterwards, we come to the first statement because we schedule a self message after start timeout. It comes to first if statement, and which is generating packet. It's kind of goes like that. For simplify all this module done, the concept we can say it reschedules itself for the subsequent packet generation after transmission completed. This is what all this done. So let's move to the bursty app.cc. And I want to start with, again, the fundamental concept. In contrast to standard traffic generators, the bursty app module simulates the behavior of real networks because it uses burst mechanism, where data is transmitted in sudden bursts rather than uniformly, just like a network protocols we deal in our real life. And for examining main idea in short way, we can say it simulates a source of bursty packets. So let's start by analyzing it. Firstly, it set up its parameters. Then and after that, it uses a special mechanism. And for simulating this bursty mechanism, what it is? Finished state machines. It makes use of finished state machines that has the states listed below. These 4 states. First one is initial state. Second one is sleep state, which it waits for until the next bus comes, next burst comes, and active state, and the burst period during which packets are generated at intervals. And this is another word, burst period, schedule packet sent. And we have sent, which is a transient state where an individual packet is generated. And in other words, generate and send a packet. But I want to mention something in here because this is important. And send will be deleted later. It only remains inside the code for explanation and demonstration purposes of the main idea, because this statue used by the original routing project, which comes from built-in packages of OMNeT++. We deleted it, but for explaining our simulation, I rebooted it. And after giving this detail, this is all this done. Basic initializing function and using finished state in the handle message. It goes from states in the finished state missions and generate packet functions. So let's move to the L2query.cc. So let's start examining L2query by giving its definition. Its network interface is represented by L2query module, and using store and forward or optional cut-through switching. It enquires packet when the interface is busy and drops them if the query is full. This is what this module is doing. So let's start examining it. And it set up its basic parameters and variables in here, and in the initialize function it gives them a value and set is busy to false in the initialize. But things starts from after that, from handle message and start transmitting. So let's start by examining start transmitting. It gets a parameter see message, and it sets is busy to true, and afterwards sends in a line or output and emit the signal, then send the scheduled function. And in other words, what is doing it? If we busy, we have packet for send. This is what is all being. It sets the busy, then sends the packet and schedule a self message for end transmission with the timeout. So let's move to the handle message for handling incoming packets. It has some if and else statements. First if statement is for checking if message is end transmission event. If it is, it sets to false, is busy to false. And inside this if statement, we have another if else statement. If query is empty, empty query, emit the signal. If query is not empty, it will get the query message from query by using pop method. Then use start transmitting message as we mentioned earlier. And else if statement, and if checks if message arrived on line in gate. First it emits the signal, then send message to out. In other words, it sends the message to upwards. In the else statement, it means other cases or arrived on gate input in gate. It has if else. In the if statement, it checks if the messages and transmission event is scheduled, and if this condition met, it means we are currently busy, so it's just query up the packet. For querying up the packet, we have if else. It checks for the frame capacity, and later I will show how we can configure frame capacity inside the ini file to enhance our results, but in here I will just show this if statement, then emit the signal, then delete the packet because our query is full. And else, if we didn't drop the packet, in the else statement, we set up the message, insert the query. This is how this if statement is doing. But if message is not end transmission event, it means we are idle, so we can start transmitting right away. And again, it's emit the signal and is busy signal to true, and then it start transmitting message using start transmitting function. And when a packet concludes being transmitted, the subsequent packet, if any, selected from the query and transmitted. All this down can be listed as like that. And I want to move to the net file for better understanding. And first I want to mention the name, where it comes the meaning of them. In LT query, we have two queries. It is the meaning of the name for mentioning it. And we have frame capacity, default 0, max number of packets means 0, means no limit. But we change in the ini file, we will mention it later and cut the switching to false. It will use instead of store and forward. This is the look of the net file with other statistics and signal values, also gates, in out and other gates. So let's move to the routing.cc file. So I want to start with why this routing CC is important for us. It is important because it is the place where we made all the major changes in our research. Most of the changes done according to this CC file. So let's start by giving fundamental functionality explanation. In routing CC, static routing is implemented on the basis of network topology. I will examine it. So let's start by the private part. It sets up its parameters and variables. And then in the initialize function, what is important for us is this C topology. What this C topology means is we are using C topology to locate all nodes in this simulation, which returns the grab node that corresponds to the specified module in the network. And I will demonstrate what this done. And another important thing in the routing CC is this for loop by using number of nodes in our network. What this for loop done is it discovers the shortest path for each detected node, expect itself. And how it's doing is using this function to find shortest paths, but except itself by using this if statement. Index 0 means itself, and then it uses some kind of other parameter settings. Another important part for us is our handle message. In our handle message, and we have some if and if statements. First, we checked for the destination address, and When the module receives a packet, it examines its destination address. If the destination address is a local, or in other words, current node, the packet transmitted up. In here, local out transmitted up. And in other case, and it search for the destination address. If it is not found, it says not reachable, then delete the packet. And alternatively, to determine the proper outgoing get, the module consults its routing table after increasing the hop count. Then it transmits the packet by the outgate index. This is all this routing CC doing. Now I want to continue with the network scenarios for further examination. So I want to start with the net60.net, and I want to open networks, net60.net. Okay, it has 60 different nodes connected with each other in different ways, and it represents a network topology commonly known as entity backbone. Also, it has some parameter settings in here. Let's move to the net60a, net60a.net, which extends net60. What this done is make some configuration to net60 by setting a connection between RTA55 and RTA0, and it extends the net60 topology basically. And now go to the net5. It has 5 nodes, some uniform functions, store delete and data rate. And for a simulation with a 5-node network and with conditions that may cause query saturation, it can be used for that reason. Another implementation of net5 is net5 saturated query. And let's move to the net10.net. It has 10 nodes, also some uniform function. For 10-node networks with different packet sizes and increasing inter-arrival times, it can be used for that reason. Let's move to the randomgraph.net, and it has some uniform function. And what this is doing is it generates random network basically. Now move to the randommesh.net, and it creates a grid mesh topology, and by using some kind of functions defined in here. I want to mention also NetBuilder in the Builder file. Let's open it. A configuration used by the NetBuilder example to build dynamic network. Now I want to show some simulation examples I ran earlier, so let's continue. Selecting, I want to select torrent forward. Firstly, let's run the simulation a little bit faster. And I want to explain what this net60 torrent forward means. And it is some kind of variation of net60, this illustrates how performance is affected by changing modules configurations to increase delay times. This results in our simulation like each node waits for the entire packet to arrive before forwarding it. And some for detail, it checks for error and other things. And in other words, as a result, what net60 store and forward simulation done is, it makes nodes temporarily store incoming packets in a buffer, process them, error checking or other things, and then forward them to the next node. This procedure is what makes store and forward constructs with cut-through switching, where forwarding begins before entire packet is received. So let's open cut-through switching. In here, it is faster because it does not wait for entire packet to receive it. It sends packet directly without enough time for error checking and other things. And both are built upon the net60. I want to also mention net60.a. Yes. What this is doing is, it is also instance of node60 backbone. It illustrates how performance is affected by minor topology adjustments by including one crucial link between node 55, as we can open in here, and node 0. And this expands upon the original net60 model. Destination addresses is 1, 28, and 50. As we can check if we make it a little bit slower and stop it. Destination addresses and bucket 2, 150, 150, and 28. We can check in here. It's their destination addresses, as we can see, also 50 in here. As a result, when we generate a new packet, the packet generated will be transmitted to one of the target nodes defined earlier in the configuration code. These target nodes are the first 28 and 58 nodes, and also we can change these target nodes in the configuration code in the ini file. Let's open ini file. Where is it? It's there. And let's fix the destination address configured manually. So let's continue with analyzing changes we have done. Implementations and changes we have done is basically changing modules in various ways to increase protocol's general efficiency and performance. I want to start with the routing CC because most of the changes we have done is basically made in this file. We have done some changes burst the app CC, but most of them is made in routing CC, so I want to start by routing CC. First thing we have done is by adding an if statement that looking for the central routing parameter. In here, first if statement, we make it to allow optional optimization user control through ini file. User control through ini file. And what this does is, what this kind of benefits it can give us is central routing determines whether routing paths for the network should be calculated. If true, it will done centrally. If not, will go independently by each node. This is what is done. And other one is again an if statement. To avoid redundant computations across nodes, now only node with address 0, as we defined in here, my address equals 0, computes the routing table. If it is true, rest of them will be done. If not, it will skip that. And this if statement is for eliminate unnecessary calculations on the computes destinations with address 0. And then, as we mentioned in here, we create new messages named route message and route info to efficiently share computed routes and compact data with all nodes and to encode all the routing data. And this is what is done. And there is one other in here to make all routing data should be defined in string format in here. And finally, we add, where is it? Yes, changes 5. We add a for loop to broadcast the routing message and to share data without extra CPU or memory cost. This is what is done because as we increase efficiency, it is possible to have much more data at the end. For other parts, rest of the code, remaining parts, we mostly don't change most of the things. We preserve and conclude original functionality of the routing mechanism for distributed routing mechanism and implementations. We mostly preserve the basic routing mechanism outside these lines. So let's move to the routing.net. There is a change we made. We add parameter for centralized routing. As we can see, central routing default false. To allow displaying centralized route computation via ini file, as we mentioned earlier. So let's move to the burstyapp.cc. Now I want to continue with the changes we have done in burstyapp.cc. And firstly, I want to start with the small thing we have done, which is adding this parameter. We add a new parameter to display collect stats value in runtime GUI for providing real-time feedback. And in here we can see we store collect statistics value in this variable we defined. Then we are using watch collect stats to visualize in the simulation real-time. So I want to move to the process timer switch case with the state conditions where we use finite state machines. And yes, in here. And yes, we can start by send. Other thing we have changes. We remove the send state to simplify the finished state machine. Normally there is a send message in here, we delete it. And other thing we have done is, after removing this send state, now generate packet is called directly in the active state to reduce state transmission, also written in here as a comment. And few lines upper we have other changes, and then cancel event, cancel send message before rescheduling. After that, schedules self message with send dynamic time plus sync time to remain in active state. This is the changes. And as a result, at the end, we collect end-to-end delay, hop count, and source address to enable the collection of useful metrics for analyzing packet transformation. Let's move to the burstapp.net, which is net file. And in here, we have this parameter, as we mentioned in the CC file. We add the collection stats parameter to net file to enable statistic collection unless explicitly disabled in the ini file. So let's move to the OMNeT++.ini. In the ini file, where we done most of the fine adjustments and settings to the parameters which directly affects our performance in routing protocol. And first thing we have done is setting sim time limit to 100 seconds. If we don't do that, and there will be different times every time we run the simulation, so we will collect bad results, and analyzing them will be inefficient. For avoiding this issue, we set sim time limit and CPU time limit to some constant number for analyzing proper results with certain time limit. With doing that, we will analyze every time almost same amount of data, and it will be better analyzed for comparing each run with the simulation. And another things we have done is we have defined the collect statistics here to get the results with the purpose of with the purpose of differentiate this project. We specifically set the parameter value for third host false and disable specifically for host 3. This is some kind of adjustments we have done. Collect statistics is true, only false for host 3. Then we change and add some parameter values to get greater and better results. And I want to start with the send AI time. We set the uniform value between 2 milliseconds to 5 milliseconds. And it increases the interval between packet sends, reducing congestion and potential packet loss. Rather than influencing only these parameters, it's so useful for throughput. And we find it when we experimented with changing this value slightly more set down, we find that it also affects throughput very influenced way. In other parameter is burst time. We set also to uniform value between this interval. It moderately adjusts the duration of active sending to balance load and throughput. It balances load and throughput. And another one is sleep time to this uniform interval. What this does is it introduces longer idle periods, helping the network recover and reducing sustained congestion. This is what this sleep time does. And another one is packet length to uniform 512 bytes to 2048 bytes. What this done is uses smaller, more manageable packets that are less likely to overflow low queues or cause delays. This is help us in this way. Another one is frame capacity. We increased frame capacity because enlarging buffer space to hold more packets during bursts, preventing early drops. And I want to mention something. For packet loss and packet length, prevent packet loss because of the delay. It's also doing that. And cut-through switching. We set this to true. Enables faster switching by forwarding packets before full reception and lowering latency. It also enables receiving faster results also. This is what this done. And also we manually set some destination addresses. And what this affects is it distributes traffic more evenly across multiple destinations, avoiding routing hotspots. This is what all this help us. Now we are in the final stage for our presentation about enhancements we have done in routing protocol. In this step, two datasets we obtained in our researches will be examined in this notebook, using necessary libraries and other tools to deeply analyze and demonstrate features, characteristics, and insights of this dataset to demonstrate improvements we obtained in this research. The two dataset routing project.csv original routing project, which comes from built-in routing project in OMNeT++, and routing project after that CSV, the project we built to improve performance of routing project in variety of cases will be used for analysis in this notebook. This analysis will compare routing project and routing project after by performance, efficiency, and other metrics by comparing our obtained results. This will show performance differences of independently performed topology and centralized network performance. And I want to start by general analysis and look of the dataset. I named this part like that. In the further examination, I will go specifically and more detailedly by using some kind of plottings, graphs, and other kind of scientific numerical analysis. But at the start, I will just demonstrate and show visual things in this datasets. In the first set, we import our required libraries for doing general analysis and look of the datasets, which is Matplotlib, Pandas, and NumPy. In here, I import routing results.csv with low memory files because it's a huge dataset. As you can see, 1200 this kind of rows, 12,000 some kind of row. It's a very, very huge dataset, 129,000 row. And I visualized it by the first 5 and last 5 rows. And for the new dataset, I also visualized it in the same way. And after that, we show some information about both data by using info function. In here, after data is using more memory. As we can see, memory usage increased. Because of our new configuration, which causes more data generation, here our values increased. There is more entries. As we look, total number, more entries. And other things, it shows non-null values in here. And which non-null means it has some kind of value. And we also improved our values because our new dataset includes less null values. It's some kind of other improvements we have done. Null values decrease. So let's continue. Again, we show data again, but specified intervals using ilocate. I showed the data between index 100 and 110. I done it for both datasets because of I want to first look how the dataset behaves and how it changed inside. I also done it for some kind of row 5000 to 5005 for both. It's just a demonstration and first analysis and look purposes. And here we demonstrate our values again for null values using isNA.sum function. We prove some changes that parameters show more null values due to disabled or non-triggered signals emissions under new configurations. For example, for giving example, attribute name giving more null values in our new configuration and some weights also giving more null values compared to before. And while others show and fewer nulls because new added or activated modules began reporting additional data, some values showing less null values, as we can see. And then again, using head function, we showed first 10 data for both datasets. And we come to the other chapter of this notebook, which is diving into details of specific columns for this dataset. And firstly, what I done in this chapter is demonstrating run parameter specifically for the first 5 times using head function. Then we show the data types of both data file, routing results after and routing results. We show them, each data types for each column. We have objects, floats, and also objects. We listed for both data files, as we can see for each column. For analysis purposes. Again, we demonstrate some attributes like run, type, module, attribute name, and value. We are going to examine them in here with more kind of detail. For generally describing this part, for example, as you can see, we want to describe some values, module, value, name, attribute name for compare more specifically. For count attribute, here again we can say that these parameters have more null values due to disabled or non-triggered signal emissions under new configurations, but after we decrease them by our improvements. You can check from here, it is uniquely described. And for unique, it again proves that we improve because that unique value decreased, suggests that we simplified or aggregated metrics after configuration. It is the definition for unique. Also, we can check in here and also in here for count unique values. We can check from here. And for frequency, it proves that some results were collected more frequently. We can say that from checking our results, as you can see, frequency improved. And we can check for other values. There is a drop and increase on the specific attributes. It depends on the situation we are in. And we'll go forward. I want to firstly explain what this means and what is done, because I create a column and use it for value. Okay, I will explain right now. In this section, I convert the column named value to numeric value, to numeric function by pandas. And in the dataset, if I do not do this, my system uses the describe function over the string values as it used in here. It used string function, but I want int function. I want int construction of it. And because it is recorded as a string, it is actually an integer value, but none or null values are recorded as a string by the system, which causes both an error and calling the describe function with wrong constructor. So I changed the value to numeric value and residence it as a value numeric. Coarse metric in here is used to provide this by checking errors. And here and here, instead of changing the executed row, I add the new column myself, as I mentioned, value numeric. When I finish the work, I used to perform the operation. I remove it from the dataset and return it to its original state. I dropped the column I added after using it. Then we want to demonstrate specifically just the unique values in the module column, just for its showing purpose. In here, just for showing purposes, in here module unique, showing purposes. And after that, this function is important for plotting and better understanding. After that, we plot the top 20 most frequent modules, as I defined in here, top 20, by using head20 function, because of the better match the distribution of values in the updated dataset routing results after, ensuring the y-axis scale is appropriate for the frequency counts in this new data, which may have longer or more spread out values. As you can see, for spreading out the values, it goes until the 165 for routing results, which is the previous one, with the most frequent modules, but the one we improved goes 220 in almost every module. This is the difference. It goes on the 165 maximum at the previous, but in the one we generate, it goes 220. It is the difference we made by showing the plotting graph. So let's continue with this cell. And this cell creates a new column called QName. As a data frame, it combines the module and name columns separated by dot by using string concatenation in the Python. And to form fully qualified name, as we can see, it concatenates names with dot. And this makes it easier to identify or visualize the metrics or results associated with specific modules. After that, we filter the data frame to include only rows where the type is scalar by using here only the indexes with the type scalar, and then the cell displays the first 3 rows of that filtered result using head function. And we can see the results from here. because of this filtering method, row numbers is different. So let's continue and transfer performance metrics, and also this is doing the same thing for the routing results after. Then I dropped it after using it because I don't want to add another column if I don't use later. I wanted to convert it to the original one, so I just dropped the QName column. So, and this chapter is analyzing scalar type values in our datasets with some logical manipulations and conversions. This part is for advanced analysis of datasets. We have using some specific science-specific columns based for demonstration and analyzing on our scalar values. So firstly, I want to start by these two cells. What they are doing, this code block filters scalar results for node 0, scalar values and operator for node 0, NA false. And this filtering mechanism, and selects key value columns, module, name, value as a summary value, and pivots the data to display metrics names as rows and their corresponding values across modules as a columns using pivot function. For example, index equal to name, values equal to value, columns equals to module, then prints the pivot. And this makes easier to analyze and compare performance metrics. In here, it gets null in columns and index. It can happen because we are using filtering. I did that to after dataset. Also, it also give me some empty column and index. It means this kind of filtering doesn't change between before and after. It's showing that. I want to give some key definition about itervar before I use this cell because the name is a little bit different. When the name definition of itervar is like when you run a simulation multiple times with different parameter values, those parameters are called iteration variables, or itervar for short. This is the definition of this name. So explaining what this cell doing. This code extracts and cleans scalar and iteration variable data using data type equals scalar or type equals itervar in here using arithmetic operator, and stores in this scalar routing results. After that, from the routing results data frame, it creates a qualified name, QName, and as here, using attribute name if available, or by combining module and name. If available, it will use attribute name or module name combined with name. It also ensures the value column contains numeric data by filling missing values with converged version of attribute value. PD to numerics, attribute value course, like just we did earlier, it also converts attribute value to numeric, but in here for filling missing values. And the result is cleaned and analysis ready subset of the data with the key fields such as run, type, QName, and value. That's like we can see in here. It makes us easier to analyze the dataset by using this large cell block. It will show specific rows between 8000 and 8005. I choose these numbers because I want to see some values between. And also this is doing the same thing for routing results after. And I want to mention this code block. This code reshapes the clean scalar results into white format. And where each run is a row, each QName, qualified metric name, is a column. And corresponding value fills the cell for comparing metrics across multiple runs side by side. For making analysis easier, it has all the different values like drops, routing drop sum, cut through, text byte sum, queue length time average listed for analysis. I showed last 5 ones for examining end of these datasets. Done the same thing for other one also. This code filters the cleaned scalar data to include only metrics listed in selected column. As I defined in the selected column, it has end-to-end delay max, end-to-end delay mean, Boozy, time average, drop count, drop sum, and all that. I get them from this previous cell's result. There is lots of different metrics, but I choose some specific ones to analyze more specifically. Then pivots the filtered results by using pivot function, and so that each run is a row, each selected Q name becomes a column, and the corresponding value fills the cell and defined in here. Then I put the tail in here, as we can see, for specific analysis. Done same thing for other one also. As you can see, results is different. Then for this code creates a column as a data frame by combining the module and the name columns with the dot separator, like not zero, dot packet received, etc., forming a clear identifier for each metric. It then filters the data frame to show the first few rows where the type is scalar. Then uses head function to show first few rows, helping preview scalar metrics in readable format, just like we did previously for demonstration analysis. And this is the same thing for after data frame, data file. And this one, I want to mention, this code uses assign function to add new QName column to the data frame, and by concatenating module and the name columns with dot, creating unique identifier for each metric. It then displays the first rows where the type is scalar, allowing quick look at the scalar metrics and their associated values. It's just same function with a cleaner definition. I did in this way also. Okay. Now we come to the most important part after doing all this visualization and analysis part. This is the numeric evaluations and plotting. This part will show us actual differences of these two datasets numerically. This is what we are concerning most. Variety of mathematical calculations and graph bulletins will be used to show enhancements in obtained results. Datasets will be re-imported to avoid confusion and potential errors, because we did some manipulations and all that. For preventing this kind of things and error afterwards, we will re-import everything and start like a scratch. So we will do necessary imports, and first for future analysis. And here we will write some necessary imports and configurations for future analysis. I want to explain what we add in here. We import Seaborn as CNC, used for statistical data visualization. From SciPy import starts in here, and imports the stats module from the SciPy library, which provides functions for statistical analysis. Import IPy widgets as widgets, imports the IPy widgets library, enabling interactive widgets in Jupyter Notebook. From IPython display, import display in here. Imports the display function from the IPython, allowing the display of the outputs in the Jupyter Notebook. And this code is used to enhance the appearance and readability of visualizations and numerical data, making the plots more visually appealing and the data output more precise. Necessary configurations to be able to analyze them efficiently. These are the configurations we done. And data loading and cleaning. This script loads two datasets, routing results and routing results CSV, and filters them, includes scalar metrics, and cleans data by converting relevant columns to numeric values, scalaring them, converting to numeric values, and it removes rows with missing values, extracts metrics names, it dumps them, and classifies modules into categories like queues and router or application. As we can see, the cleaned datasets are then ready for further analysis or comparison, with the final shapes of data displayed for verification. And as we can see in here, cleaned before shape, cleaned after shape, and after the summaries data, we export with specified with records and notes and metrics. Our records increase because our configuration generates more results, as we can see in here. And also in here, we can see our records increased because of our configuration generates more results, as in here we print that values. And then we compare some results visually by this function. Hop count mean before the improvement and after the improvement. And as we can see, after and before in the hop count mean, if the hop count decreases, this typically means that data travels through fewer intermediate nodes, as we can see, and leading to potential faster and more efficient routing. In end-to-end delay mean, before the improvement, the delay spikes due to network instability, and while after the improvement the delay is generally lower, but still experiences occasional spikes due to the external factors. And drop count, fewer dropped packets suggests better reliability in the network, which could be a result of improved protocols or a better network management. And TX byte sum in here, an increase in the amount of data transmitted could indicate that the system is handling more traffic or transmitting larger payloads successfully, as we can see. And RX byte sum, a rise in received bytes suggests that the network is able to handle a larger volume of incoming traffic or that more data is successfully being received. And there is some numeric explanations which is the same values according to these graphs, which is just numeric visualization of it. And for core metric analysis, detailed performance evaluation across K metrics. And here again, as we look output of this function, we have nearly the same plot tables due to the previous one. They are important because of that. At the end, these tables will be examined more clearly. Let's move to the throughput analysis. The analyzed throughput function compares transmitted and received bytes between the before and after datasets using box plots. And it also performs a mean Whitney U-test to assess the statistical significance of differences in throughput for both metrics and prints the p-value. This analysis helps visualize the evaluate change in the network throughput. For example, we can see transmitted by comparisons by after there is lots of more, and received bytes there is much more bytes compared to before and after. Also some p-values. Let's move to the latency analysis. This part compares latency difference distribution between the before and after datasets using cumulative distribution plots. It also analyzes the relationship between latency and throughput in the after, providing insights into how latency changes and its correlation with throughput, as we can see in here before and after. And blue one has wider spread, which is before, showing high latency. After one rises more quickly. Means that most latency values are lowered and clustered compared to previous one. This means better results after, and also we have latency versus throughput graphic in here. And we have queue analysis. Queue analysis function compares query length, distribution, and utilization, uses a violin plot to show the distribution of queue length. And queue length time average parameter between the before and after datasets, and a plot and line plot to illustrate query utilization over time. And this analysis highlights changes in query behavior across the datasets. This is important. And in the before datasets, there is an extraordinary outliers. Query length goes up to nearly above to 7,000 and less than 8,000, which plotted like a thin line in our graph, and compressed appearance for rest of the data in here, compressed look. In the after, smaller query length, there is a little bit length in here, shows significant improvements in query management and ended up less congestion and delay in the system. And also we have query utilization timeline graph. And for moving to correlation analysis, correlation analysis function compares correlation between metrics in the before and after datasets. It merges the datasets by a module and computes a cross-correlation matrix between corresponding metrics. And a heat map visualizes these correlations. It's a heat map. Statistical relationship of different values between them, like when one variable goes up, other goes up, or opposite of that. There is a linear relationship in the correlation heat map, highlighting how relationship between metrics have changed after the update. And correlation heat map shows K-metrics changes between the datasets. And we can say that correlation heat map shows query, hop count, the delay shifted significantly. If we match, for example, higher values, we can recognize hop count max and other parameters like that. And after the changes, this demonstrates that our changes made system faster, more stable, and less congested. So let's go to the statistical report. The enhanced statistical report function provides detailed comparison of a k-matrix between before and after dataset. It includes mean percentage change, significance test. This report also uses t-test and mean Whitney U to check statistical significance, cohen's d to measure effect size, and CLS to show the likelihood one group outperforms the other. For examining it better, we can check the data it gives us. For looking to hop count, there is no meaningful decline in hop count, so little to consider, but in the end-to-end delay, we achieve significant and meaningful effect. And for the drop, if we check that number, it looks like increase in positive way in the obtained value for drop, but in contradiction, it improved very effectively and meaningfully. It's just for demonstration purposes. It does not affect or not causing slowing or dropping packets. And even if it seems it's good thing, it seems positive and good thing, not meaning drops increased it, that percentage, if we checked PU test and other tests for the percentage. In TX bytes, we have small but meaningful increase, 8.64. In BUZI, we have much largely increased, as we can see in here, but for analyzing it more meaningfully between relationship between BUZI and TX bytes, we can say that from both way, because of the correlation between each other, we can give example like if received and transmitted packet increases, the higher use of resources will come as consequence of that. We can say from this matrix, we can conclude it like that. Let's move to the final evaluation report. The generate final report function presents k-metric improvements by showing both absolute and percentage changes, along with effect sizes, which is cohen's d. It uses a bar plot to visually compare relative gains and strength of changes, helping to clearly identify the most impactful performance improvements. As we can see, there is a box plottings in there. Also, numeric changes. This is what we concern most. So let's dive into deeply. Routing efficiency reduced by this percentage, possibly due to traffic or unreliable network packet might not be taken, the idle nodes. And this is the relative result. For latency, just we mentioned earlier, it's minus but increase by this percentage. This indicates that packet forwarding might be postponed because we are utilizing inefficient routing. In our traffic generation, it can be considered not that meaningful because of this minus sign it has. But our latency is significantly decreased. We performed our latency metric. It's better result. And we declined packet loss in a very efficient way for monitoring. For mentioning, we don't have minus sign in there, but this should not cause misunderstanding. And this sharp decline in packet loss caused by much better network capabilities, fewer packets rejected, improved user experience, and data integrity. It's a better result at various cases. And for explaining throughput, there is very noticeable improvement in throughput module, reflected by this percentage, indicating network messages data more effectively. In query utilization, it is again showing minus in here, but it is improvement. This improvement in query utilization indicates improved usage of resources of the network and much effective buffering, which improved traffic flow and cut down idle time. As a result, this final report, this is most significant part for evaluating our results. This matrix is show what we done actually. The final result is most important one for us, and we show what we done in here. And performance in the routing project is evaluated mostly in here by us. And this is the end of the analysis we done in our routing project, evaluations, analysis, and all that we made. in here. After the changes we made, this is what we made by enhancements for routing protocol.